Good morning, all. Welcome to third lecture of Unit 3. Today we are going to discuss about carrier generation and recombination. So it can be considered as a common point in all the types of semiconductors. So when sufficient energy is given to the semiconducting material, covalent bonds are broken and a pair of electron and hole is generated. So these concepts we have already discussed in second unit under the topic of semiconductors, like what happens when energy is given to a semiconducting material. But again, we recall here, the electrons are raised from valency band to the conduction band and holes remain in the valency band. So whenever a covalent bond is broken, the bonded electron become free electron, and the free electron, once gaining the energy greater than this forbidden gap, then go to the conduction band. So that free electron now act as a conduction electron in the conduction band, and the space that is left over in this bonded broken will act as a hole. So the process of generation can occur only when the energy given to the semiconducting material is greater than its forbidden energy gap. Recombination is the process where an electron from the conduction band recombines with a hole in the valency band. So this generation and recombination is a continuous process when the energy is supplied to any of the semiconducting material. So that's why in the semiconductors, there is always a chance of creating two types of charge carriers. One, a hole in the valency band, and other one, an electron in the conduction band, which is not taken in the case of metals, though they are good conductors. So this is called band-to-band recombination, and in this process, a photon is released. Now, in how many ways the recombination can take place means it completely depends on the type of the semiconducting material that we take. So they can be classified as direct recombination and indirect recombination. So in direct band gap materials, if you see, this is the structure which we can see in the direct band gap semiconductors. So this structure is seen in the case of gallium arsenide, gallium stibbatine, indium arsenide, indium stibbatine, cadmium sulfide, and so on. So if this picture can be understood like if this is the valency band and this is the conduction band, there will be a continuous discrete energy states. Now if you see the topmost energy state of the valency band and bottommost energy state of the conduction band, both occur at the same value of momentum vector, then we say such material as direct band gap semiconductor. So now we can say that since these two energies means the topmost of VB and bottommost of CB are in matching with each other, then in such materials, if there is a chance of recombination and generation of charge carriers, the difference in the energies are liberated in terms of light. Means we can say the photon energy is liberated. So this type of direct band gap materials are used in devices where we can see the light as an output. So examples are LEDs. LED will give the light as an output, photodiode, photodetector, laser diode, and so on. Similarly, if you see the indirect band gap semiconductors, the structure will be the topmost of the valency band and the bottommost of the conduction band are not in matching with each other. They occur at different momentum vectors. So that's why when the recombination takes place in this type of materials, then the difference in the energies are liberated in terms of phonons or heat. So that's why due to this difference in the momentum, the probability of direct electron hole recombination is less in the case of indirect band gap semiconductors. So where we can see this type of indirect band gap semiconductors is in germanium, silicon, gallium phosphide, lead sulfide, and so on. That's why if we make a diode by using germanium or silicon, we can see the heat that is coming out on operation, but we can't see the light as an output. So the amount of light emitted is directly proportional to the forward current. So the mechanism is less in the indirect band gap semiconductors. So we can see the output in terms of heat, whereas in the direct band gap semiconductors, we can see the light as an output. So in this class, we have discussed about generation and recombination definitions, how it happens in the case of semiconductors, then the types of recombinations, that is direct and indirect band gap semiconductors. So as a clue, we can say that in the next coming topics of all the optoelectronic devices, we are going to study about direct band gap semiconductors where we can see the light as an output. Thank you.